The purpose of this lab is to understand the motion of a falling object, to analyze the distinctions between an object under constant forces versus non-constant forces, and to explain what terminal velocity means in the context of a falling object. First, we must discuss physics concepts that are fundamental to this phenomenon. Newton's second law is crucial because it shows the relationship between net force and velocity and position. In the case of an object in free fall, our first model, the net force is the gravitational force. However, in this lab, we also want to understand whether or not turbulent drag or air resistance, a force which acts in the direction opposite of motion, is in effect. Therefore, in a secondary model, we will also include the drag force in the calculations of net force. It's also important to note that when gravity is acting near the surface of the Earth, the net force on the object is constant. However, with drag, since drag is dependent on the magnitude of velocity, the net force is non-constant. So we will need to account for these differences in our position update formulas. At the start of this experiment, I held an object with a large area, a glider, about a meter in the air and released it from rest. At this exact point in time, the velocity was 0, the net force was 0, and the position was at the origin. It's also important to note that the system is the glider and the surroundings are the air and the floor. As a brief preview, the lab results show that the glider was not in freefall, since the observed position data more closely resembled that of an object that has a net force, drag. This makes sense since the glider has a large surface area and air resistance is far from negligible. To start, I filmed the glider falling from rest. Then I uploaded the video to Tracker, which gave me the necessary position versus time data. I decided to ignore X position for the purpose of this lab because the object's position should only be changing in the Y direction. Then it was time to set up two different computational models, one with gravity only and one with both gravity and drag. While making those models, I kept in mind a few assumptions. For gravity only, I assumed that the object was in freefall, that there was a constant force acting on the object, and that gravitation was the only effective force. For gravity with drag, I assumed the object was not freely falling, that there was a non-constant force acting on the ball, and that the object had only two forces acting on it. For the glow script code that only included gravity, I therefore decided to set net force equal to gravitational force and used Newton's second law for the velocity update formula and the constant force position update formula. For the code that included both gravity and drag, I set net force equal to the gravitational force and the drag force, and this time I used the non-constant force position update formula. From these models and the tracker data, I arrived at these results which exhibit notable differences between each other, especially in the velocity versus time graphs. When I put all three models together, the differences became even clearer. However, there is more difference between the observed motion and the predicted freefall motion compared to the predicted drag motion. Therefore, it is safe to say that the object is not in freefall and drag was a contributing factor in this motion. Analyzing the data even further, we see that even though the glider was under the effect of drag, the graphs did not line up perfectly. Possible sources of error include inaccuracies in the translation of the observed position by the tracker, as well as inaccurate estimation of mass. It's also important to note that the drag coefficient B was calculated by calibrating the final Y position in the predicted drag simulation, so it may not be completely accurate. Despite these discrepancies, the model still helps us understand terminal velocity, which is the velocity an object reaches when the drag force balances with the gravitational force. Looking at the velocity versus time graph with drag, we can see that though the change in velocity is not constant, the velocity does eventually level out and become constant. If the force was constant throughout the motion, this would indicate that zero net force is happening, which is what happens during terminal velocity. This phenomena is not exhibited in the velocity versus time graph without drag. But what if we were to start the object from an initial velocity that was less than zero? Will the terminal velocity stay the same? Well, using the drag model, I tried different initial velocities each time getting the same final velocity. So I kept doing this until I got an initial velocity at which the velocity was constant throughout the entire motion. This velocity is the terminal velocity, and shows that regardless of the initial velocity, the terminal velocity will not change. This is because the gravitational force does not change, and so when the net force is zero, the magnitude of velocity will always be the same.